Hello and a warm welcome to each one of you. It's my pleasure to welcome you to today's webinar, Calculate Your Project's Embedded Carbon in Part 9 Construction with the Material Carbon Emissions Estimator, MCE2. I'm Felix, the webinar coordinator from the Continuing Education Department at the OAA, and I'm happy to facilitate today's session. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from today. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we commence, I would like to share some important information to ensure an effective and professional webinar experience. Please be informed that this session is being recorded for quality and educational purposes. In order to maintain a stable internet connection, we have muted all participant microphones and disabled video feeds. We highly encourage engagement through our Q&A window. Feel free to submit any questions you may have for our speaker. These will be addressed in the designated question and answer period at the end of the presentation. Kindly note, the chat function will be deactivated following this introduction, except when needed for responding to questions during the webinar. For those seeking continuing education learning hours, please note that attendance is crucial. A minimum of 80% attendance is required for these hours to be accredited to your transcript. Please allow up to a few weeks for the processing and reporting of these hours. And lastly, please note that the presenter does not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. For accessibility, we provide automated closed captioning services available in multiple languages to accommodate the needs of our diverse audience. And now, I'm excited to introduce you to our speaker for today's session. Please welcome Tom Davis. Tom Davis is a professor of building technology at the president of Green Tech Environmental Engineering with over 35 years of experience in education, research, consulting, real estate development, design, construction, and project management for heavy construction projects around the world. Tom is also a principal investigator in applied research responsible for all aspects of research design and testing. He is a licensed professional engineer in Ontario and the United States. Tom is also a lead accredited professional for building design and construction with the Canadian Green Building Council. Thank you very much for your attention. Let us now proceed with the session, and I'm passing it over to you.
Thank you very much, Felix. Welcome, everyone. I'm delighted actually to see the number of attendees. People are still, I think, dropping into the session at 109. Fantastic. So we've got quite a journey for everyone today. So I'm going to go ahead and get my screen set up. And really introduce you to the Material Carbon Emissions Estimator software, I guess, sort of introduction and tune-up. Really trying to get the whole notion of carbon, under control, get our minds around it, and to really just set the planetary goal here is that we need to be emitting zero carbon into our atmosphere by 2050. So in the not too distant future, we're looking at changes to national building codes beginning in 2025 for operational carbon and 2030 for embodied carbon. We'll be talking about both of those topics here today. So just to go ahead and launch into the training, MCE squared is designed for Canada's home building industry. It quantifies the greenhouse gas emissions associated with specific low-rise residential building designs by providing two important estimates: the greenhouse gas emissions associated with manufacturing required building materials, and the estimated greenhouse gas emissions from operating the home calculated using results from HOT 2000 energy models. Together, these results predict the overall greenhouse gas impact of the climate on the climate of a new home or a renovation, its carbon use intensity or CUI, and provides industry with insights for reduction opportunities. So today's agenda is really, geared again toward the home building industry, part 9 type of construction. It quantifies the greenhouse gas emissions associated with specific low-rise residential building designs by providing 2 important estimates: the greenhouse gas emissions associated with manufacturing required building materials, and 2, the estimated greenhouse gas emissions from operating the home, calculated from the results of HOT 2000 energy model. Together, these results will predict the overall greenhouse gas impact on the climate of a new home, or importantly, to underline a renovation, its carbon use intensity, and provides industry with insights for reduction opportunities. MCE squared was designed for Canada's home building industry. Oops, sorry. And we're going to be looking at teasing out the differences between operational and embodied carbon. We're going to calculate some carbon emissions for materials using some software generated by Natural Resources Canada and is available free of charge. By way of full disclosure, I should also indicate that, yes, I am a college professor, but I'm about halfway through a 1-year sabbatical, and I am embedded with the folks here at NRCan, or Natural Resources Canada, as shown here in the bottom of the page. Sorry, my little scribe is going a little bit wild over here. Let me just see if I can get that thing dialed in. Oops, that's not dialed in. Okay. So MCE squared, Materials Carbon Embedded Estimator. It's an Excel-based tool. As previously indicated, it's free of charge. I will be providing a URL and a link to download the software a little bit later today. As previously indicated, it also works quite well with HOT 2000, which is the energy modeling software also developed by our friends at Natural Resources Canada. Primarily, we're focused again on Part 9 construction, low-rise to multi-unit residential buildings, or MERBs. Again, new construction or retrofit. A little bit of context for what's happening here today and what's going to be happening in the future is that the Canadian government's in its early stages of creating codes and thresholds for embodied carbon in buildings. Cities like Vancouver and Toronto have introduced voluntary embodied carbon measures and will move toward regulation. Understanding embodied carbon and MCE square tool will enable leaders in the industry to anticipate and prepare for future regulations. So again, we see embodied carbon coming in the National Building Code in 2030 and operational in 2025. So a lot happening, and I guess I should back up a step. The whole motivation and the impetus behind this entire initiative is to save the planet that we're, depending on for our own well-being and future. Designers and builders are familiar with energy efficiency concepts, building with more insulation, improved air tightness, and efficient mechanical systems. Today, we're starting to prioritize the emissions associated with energy, not just the energy use. Until recently, the amount of energy required was an important metric. But now we know that the same amount of energy creates different impacts of greenhouse gas emissions depending on the fuel source used to create the energy. This creates two pathways for reducing emissions using less energy and using cleaner energy. These can be combined or pursued separately depending on local conditions. Operational carbon emissions, we'll call them OCE in this presentation, are measured in kilograms of carbon dioxide equivalent. We'll explain these terms also to you a bit later. So again, operational carbon here, and we can calculate that with a similar tool, HOT 2000. It's an Excel-based program provided by Natural Resources Canada. Once you do your energy models, we can import the results, your operational carbon, directly into MCE squared. Okay, so we get our energy consumption from HOT 2000. Then what we need to do is use source emissions. Our grids make different levels of clean power. Some make dirty power. So where we're using electricity matters, because it matters as to how that electricity is generated. Okay, so we can make it more energy efficient. And I say two things there. We plug the holes. We bring the air changes per hour down to 1.5 or less. And we can also burn a cleaner fuel. The cleanest, greenest fuel of our future is or will be electricity. Again, not all parts of the country are at that stage today, so it's important to understand where you are and the grid intensity or the carbon intensity of the grid electricity that you're using. So let's take a look at some examples of operational carbon emissions based on a two-story house in Toronto. This type of model will be different depending on location, as the greenhouse gas intensity of the electrical grid varies by location. The assumptions for fuel-related emissions are built into HOT 2000 and MCE squared. So you can generate this sort of analysis for any location in Canada within these tools. In this example, the y-axis is showing tons of CO2 equivalent emissions, and the x-axis is showing years, with the date of occupation of the house as year 0 and moving to 30 years into the future. Using a mix of gas for heat and hot water production and electricity for all other loads, a house meeting building code requirements for energy efficiency would generate about 3.5 tons of emissions per year. Cast forward, this will accumulate to 104 tons over the next 30 years. And note that this does not assume that the factor for electricity generation is becoming cleaner in the future, although it needs to become cleaner in the future. So starting out in year 1, we have no operational emissions. We walk in and turn on the lights for the first time, and every year thereafter, we add 3.5 tons of emissions to the atmosphere, global warming emissions. Currently on our planet, we're dumping 162 million tons of CO2 equivalent into our atmosphere every 24 hours. This example demonstrates the same two-story house with two important changes. The energy efficiency of the house has been improved to meet net zero ready, or tier 5 levels of energy efficiency. Tier code is coming your way. And number 2, the house is all electric, using heat pumps for space heating and hot water production. This has changed the emission profile of this house significantly, reducing the annual emissions to 0.44 tons per year and a 30-year total to just 13 tons. It's important to note that this kind of result is possible in provinces with relatively clean electrical grids like Quebec, Ontario, Manitoba, and BC. In provinces with a lot of coal-fired energy generation, the emissions impact of electrifying the building will be less, and in some places today may be no better than using gas. However, as these grids are cleaned, all electric houses will have a better result. So we're going from 104 tons under a business as usual scenario to almost a tenth of that by applying a few simple rules. So what we want to do is make our building energy efficient before we size the mechanical equipment. So we do energy efficiency upgrades, and we can determine which ones using HOT 2000. It could be just windows, it could be exterior cladding, exterior continuous insulation are examples of retrofits that I've done here in London, Ontario to achieve 20% or 70% energy reduction. The nice thing, if you can remove 70% of the demand from your home, the remaining 30% of the energy that is required can be very easily made up with solar photovoltaics or a net zero construction. Operational carbon emissions are relatively well understood, and in the coming years, Canadian building codes will pivot to make emissions the metric used to assess performance rather than energy consumption. Okay, when? 2025. But focusing only on operational carbon emissions, while critically important, misses an important part of the emissions story for new homes and retrofit homes, I should mention. Measuring OCE assumes that the house starts at 0 emissions on day 1. However, emissions are also generated to manufacture all the materials required to make the house in the first place. These are called embodied carbon emissions or material carbon emissions, MCE. On this graph, we're showing a yellow arrow at year 0, and this indicates the upfront emissions. If we don't know the amount of MCE, we really don't know the full climate impact of the house. Whatever the MCE might be, the house will carry that carbon footprint with it into the future. And all the operational carbon emission needs to be added to that first burst of material-related emissions. MCE squared is designed to help us understand and estimate the height of this yellow line so that we can see the full emissions profile of the house. So again, I refer to it as the day that you open the front door for the first time. This design has resulted in 60, let's go over here and read the metrics, 60 tons of CO2, and that little e means equivalent. We have to, all gas emissions are not created equal, so we have to equate them to carbon and its greenhouse gas or global warming potential. And then we are comparing apples to apples equivalent numbers, okay? So if we're starting out at 60 and we're adding our 13.2 tons per year, you get this original 60, right? Oh, I'm sorry, not per year. That's over 30 years, plus 13.2. So we have 73.2 tons CO2 equivalent per year, or a total over the 30-year period. Sorry, I misspoke there. Now let's look at the carbon material emissions, or MCE. Building products can generate greenhouse gas emissions at every stage of their life cycle, from first extraction of raw materials until the end of their life. Life cycle assessments, known as LCAs, divides the full life cycle of the products into distinct stages using alphanumeric numbering system to label each stage from A1 to C4, as you can see on the slide. A stage includes the steps from getting from a raw material to a finished product installed in the building. B stage covers the use and maintenance of the product or building. C stage covers the end of life cycle emissions. What I like to talk about here when we shift from operational, we want to drive our operational carbon down to near 0 anyway, right? But if we ignore the material carbon emissions, once those emissions end up in our atmosphere, that carbon is in the air for over 100 years. So on day 0 of every one of our buildings, in the case just stipulated 60 tons are released into the atmosphere. That could be more than 50 or 60 years of operational carbon. So imagine that our planet is a medical patient on life support. Why? Because it is. And you're the physician that's being brought in to save the planet. If carbon is the problem, adding huge slugs of carbon up front as we build or retrofit buildings is a bigger problem if we don't understand what those material emissions are. The way I put it in medical terms is we want to make sure that the cure, i.e. making these buildings efficient, doesn't kill the planet. We don't want to have all these upfront emissions outstripping our operational emissions savings over the 30 years. The MCE data and MCE squared includes the A1 to A3 stages of life cycle assessment. We call that's known as the product stage. We also refer to that as a cradle to gate. So imagining when you excavate the raw materials, you transport the raw, in this case, maybe it's lumber or some ore. We ship that to a manufacturing location where it's produced, and we call this cradle to gate emissions, and the gate being the factory gate. So we can with pretty good precision get our head around this cradle to gate emissions. And why are we focusing on that in the MCE squared? 65 to 85% of all of the material emissions happen in this stage. The remaining percentages are made up during the construction phases, the operation and maintenance of the building, which can be over the lifespan of 15 to 50 years. And then at the end of life cycle, another 3 to 15% carbon emissions just by caused by recycling and reusing building components. Still a good idea though. Okay, so I did this math for you a couple moments ago. So all we did is took that where it starts at day one at 0, took that line and we just moved it up and added that to the 60. So we started out with 60, not 0, and then we increase our incremental amount for operational carbon. We add that to the original carbon. So you can see over 13 years, the carbon to condition the air and the water in that home is roughly, a quarter of what carbon emitted to bring the home into existence in the first place. We don't want the cure to kill the patient. Okay, so the results for MCE can vary wildly, as building products have very different emissions profiles. As shown on this slide, it's possible to get emissions as high as 120 tons for a typical 2-story house, or as low as 10 tons, or anywhere in between, even if the level of energy efficiency is the same. Why the big difference? Well, it's the materials that we use. This has a huge impact on the carbon use intensity of a house. In a worst case scenario, MCE is the dominant part of the carbon footprint. In the best case scenario, it's less than half of the carbon use intensity after 30 years. We want you to be able to use this tool so that you can understand and share with your clients the MCE impact of a house design and help avoid the worst outcomes and encourage the best ones. So by making smart material choices, we can reduce the initial carbon emissions at day 0 by 110 tons. That's significant, especially when we look at the operational carbon as being 13 tons over 30 years. We could burn coal in that house for 30 years and it would still be, more efficient than building that 120-ton material choice house up front. The results of the embodied carbon analysis are expressed as a mass of carbon dioxide equivalents, okay? We want to compare apples to apples and oranges to oranges. This means that all greenhouse gases that contribute to global warming are accounted for, like refrigerants as an example, but their unique impacts on the climate are expressed as the impact of the proportional quantity of carbon dioxide, or CO2 equivalents. We can examine embodied carbon of a whole house so that we're looking at the material carbon emissions. This is expressed in metric tons of CO2 equivalent. This tells us about the gross impact of a particular home on a climate. We can also examine embodied carbon intensity of a home so that we are looking at the material carbon intensity, or MCI. This is expressed as kilograms of CO2 per square meter of your building. We can look at total square meters of floor area, or we can look at square meters of conditioned floor area. Most often we look at conditioned floor area because it prioritizes living spaces and penalizes embodied carbon expended for things like garages and unconditioned basement spaces. If we only look at MCI by total floor area, the lower embodied carbon that is typical of less finished areas like garages and basements actually makes the carbon use intensity look better. To prevent incentivizing adding more low carbon spaces to have a positive impact on MCI, we choose to focus on the material carbon impact per square meter of conditioned floor area. This is also the approach municipalities and early adopters of embodied carbon incentives and regulations are using. All MCI figures quoted in this presentation are the material carbon intensity per square meter, and in this case, conditioned floor area. Understanding the material carbon emissions for an individual house helps us estimate the impact of the material related emissions on our national climate targets. In 2021, Builders for Climate Action did a study for Natural Resources Canada, the group I'm working for, or with, I should say, that estimated the MCE at 250 kilograms of CO2 equivalent of per square meter of conditioned floor area. At that quantity of emissions per house, the average construction of a new home in Canada is generating just over 14 million tons of greenhouse gases every year. So that has nothing to do with the operation of the homes. This is just bringing them into existence. That's the equivalent of tailpipe emissions from 3.1 million cars, or emissions from 3.6 coal-fired power plants. For context, the province of Ontario closed 4 coal-fired plants in 2014. That was the single largest greenhouse gas reduction in North America. The home building sector in Canada has potential to make this large an impact every year. But first, we need to learn how to use tools like MCE squared to estimate and then reduce emissions. Chris Magwood and Builders for Climate Action used MCE squared and its sister tool BEAM to estimate the MCE and carbon intensity of 550 as-built new homes across Canada in 3 different studies. They found a wide range of results across these studies, but the results point to some general conclusions. At the high end, so the figures shown in red over here, using high impact materials, the material carbon intensity can range from 300 to 550 kilograms of CO2 per square meter. At the low end, the carbon use intensity could be from 72, which is the low one here, to 138, which was the high one for that category. The averages of all the buildings in each study show a range from 150 to 194 kilograms of CO2 equivalent per square meter. And we're relatively consistent despite differences in climate, location, and building style. From these studies, we can begin to see that there's relatively consistent average among new homes in Canada, but also that it's possible to, pardon me, it's also possible to achieve results that are either much higher or much lower than this average. It's encouraging to see that some builders are beating the average by 30 to 50% without even trying. This means that there's a lot of low-hanging fruit to be found in conventional building practices, and that in theory, every building could be beating the average by a substantial amount. And that's our goal. And toward the end of this presentation, we'll talk about logical steps that can be taken, starting immediately and, subsequent years after 2024. Okay, so as we explore the MCE tool today, you'll see that it can be used in many different ways. MCE Square provides comparative insights between material types and product choices that serve the same function. For example, cavity insulation as shown in the snapshot. That can make the difference between a high embodied carbon and a low embodied carbon home. So here you can see that not all insulation materials, just looking at the net emissions category on the far right, they range from, let's call it 9,600 to or as high as 58,000, or as low as negative 19,000. And how do we get a negative emissions number? We use a building product that once grew and absorbed carbon out of the atmosphere and took it into that building product, and we're taking that building product and locking it into your home. So we're sequestering carbon. MCE Square can be used to make embodied carbon comparisons of different assemblies within the building by combining all the materials required to build a complete assembly. For example, an exterior wall assembly that includes cladding, strapping, sheathing, framing, insulation, and interior finishes. You can compare completely different but functionally equivalent assemblies. For example, an exterior wall assembly that is wood framed compared to one that is made with insulated concrete forms or structurally insulated panels. Or compare the impact of switching just one or two materials within a similar assembly. For example, a wood frame wall, but with different types of insulation or cladding. MCE Squared can be used for the design development to gain insights into the embodied carbon differences between options, such as a bungalow design versus a two-story version of the same interior square footage. MCE can also be used to create whole home building models and to make comparison between design options with only a few small material changes, such as roofing and flooring swaps, or options with very different construction types, such as masonry building with a flat roof compared to a wood frame building with a pitched roof. The connection with HOT 2000 allows you to see the operational carbon emissions, the OCE, of the building alongside the material carbon emissions and calculates the carbon use intensity over a 30-year period. The basics of estimating material carbon emissions are quite straightforward. And at its simplest, MCE is the product of multiplying a quantity of a material by the global warming potential GWP factor for that type of material. These global warming potential factors come from another acronym called Environmental Product Declaration. So we'll be talking about those later. So that's where we extract that information. For MCE Squared, it has 10,000 EPDs in its database. So we have the global warming potential for 10,000 different building materials. Is that all of them? No, but it's a good start. And there's a lot of opportunity to reduce that going forward. So where did the data come from? internal calculations to determine material quantities based on the dimensions the user inputs into the tool. For example, user inputs of the area of exterior wall, and MCE will use that dimension to calculate the amount of framing, lumber, insulation, interior finish, and exterior cladding required to build that much area of an exterior wall. The tool uses industry standards for converting area into material quantities. MCE has a database of global warming potential factors for materials common to residential construction. These global warming potential factors come from EPDs, which we'll discuss in the next slide. EPDs give global warming potential factors for a certain quantity of material, and the MCE squared converts those factors to the correct amount of material for the building model. We'll look at some examples of how this works a bit later. All of this is happening behind the scenes while you're looking at an embodied carbon result in MCE. All of the above calculations have taken place. It's important to understand where this information comes from, and we, use or describe EPDs and compare them to nutrition labels that you'd find on food products. They contain numerous environmental impact categories. Material carbon emissions only considers global warming potential. EPDs are created according to ISO and EN standards so that they're prepared the same way for all types of products to ensure that the same set of impacts are considered in the same way. They set boundaries for the study and determine what kinds of data can be used. Although there are some differences between EPDs in terms of data quality, they are the best system for understanding global warming potential, and the rules for making EPDs continue to be refined and harmonized to produce better and more comparable EPDs. Environmental product declarations must be renewed at least every 5 years. The most reliable EPDs are referred to as type 3 EPDs, which means they have been verified by a third party. Not only has the manufacturer gathered all the information together, but it's been verified by a third party, so it's much more reliable. The majority of data in MCE squared comes from type 3 EPDs. When this is not the case, there are notes in the tool to make clear that some data comes from different sources, and we'll identify those sources. EPDs have really only come into use in construction in the last 10 years, and today there are fewer products with EPDs than without. EPDs are publicly available documents. Anyone can go to these sources of documents and perform their own embodied carbon calculations. But it can be difficult to compare EPD results because the results are often given in different terms. For example, the EPD for brick cladding might give you the global warming potential result for a kilogram of brick, while the EPD for wood siding might give you the global warming potential that might result from a square meter of siding at a given thickness, like 3/4 inch. You cannot compare these EPDs unless you convert them to functionally comparable amounts of materials, square meters of materials, not, the weight of the brick, for example. Those calculations and conversions take place behind the scenes within MCE. Why? So again, we can compare apples to apples. MCE squared includes 2 distinct types of EPDs, and it's important to understand the difference between them so that you can more accurately interpret these results. As we explore the tool later in this course, we'll show you how the tool makes it easy to identify the type of EPD. Industry-wide EPDs are created by the industry associations. The clue is in the name, right? Industry-wide. They use data from a number of different manufacturers of the same product type to create an average global warming factor for all products in that category. Are they precisely accurate? No, because you don't have a specific product in mind but it will represent, average products from that category. This type of EPD is useful for understanding the relative difference in MCE between one material category and another. Because the global warming potential results of industry-wide EPD are an average for multiple manufacturers, the user will not know if the specific product used in the project might come from a manufacturer with global warming potential that is higher or lower than the average. And that's, these generic results, we have to be very mindful of that. Where it may be helpful in the early stages, once we get into design development and we start to select specific products, go to those product specific EPDs and you'll get more accurate estimates of your embodied carbon. Manufacturer specific EPDs cover a particular product or product range from a single manufacturer. Enables more accurate comparisons, but assumes that you know which product might be used in the project when you're making the model in MCE squared. MCE squared also provides users with an average that is calculated from all manufacturer-specific EPDs in the product category. We'll cover more on that option when we examine the tool. EPDs can also account for biogenic carbon stored in products that are plant-based. Again, these materials could have carbon negative numbers. The inclusion of the carbon storage is based on the CO2 that plants draw out of the atmosphere during photosynthesis. They take atmospheric CO2, use the carbon atoms to create the structure of the plant and sugars for the plant, and it releases the oxygen back to the atmosphere. The amount of carbon stored varies by plant species, but generally ranges from 35 to 55% of the dry mass of the material being used. This provides a type of carbon dioxide removal, CRD, that is recognized by another acronym, IPCC, the Intergovernmental Panel on Climate Change, which is an organization of the United Nations that looks at all climate data generated everywhere on the planet as being an important part of meeting global targets, this carbon dioxide removal or sequestration. Because when the carbon held in plants is prevented from returning to the atmosphere due to being eaten, burned, or decayed, it reduces the overall CO2 burden in the atmosphere. Buildings can provide a durable, safe place for carbon to be stored, and so the flow of biogenic carbon is often captured in EPDs. I'll also mention it is often not captured. In this software, if it isn't captured in the EPD, we try to make our own calculations to determine carbon storage. Rules for creating EPDs do not require that biogenic carbon to be counted. So not every EPD for a product with biogenic carbon will include these data. And MCE squared factors for carbon storage have been added for products that contain biogenic carbon but do not declare it in their EPDs. They didn't put their best foot forward, right? The same ISO methodology for calculating biogenic carbon is used to do this. This ensures that all products within the biogenic carbon are treated in the same way within the tool. The current version of MCE squared does not include biogenic carbon storage figures for virgin timber products, even though they do contain biogenic carbon. This is a judgment call. We're constantly debating it, and it's based on the scientific uncertainty about the climate impacts of forestry and the definitions of sustainable forestry used to differentiate between products harvested in a way that damage the climate versus helping the climate. The next version of MCE square will allow the user to decide whether or not to include carbon storage values for these products. So on this slide, so that what I just finished talking about is the timber. Maybe it's carbon negative. Well, it depends on how it's harvested and manufactured, transported. It could be, carbon negative. significantly or significantly carbon positive. Things that grow and are oftentimes turned into building materials: straw, hemp, hulls and shells of nuts, for example, or coca beans, stalks like straw from wheat crops, purpose-grown crops, cork, reeds, waste stream. So we use waste paper to make cellulose. So that's a really good carbon negative product. Or we can use microbes to produce building materials, which is being worked on in the future. The nice thing is that all of those calculations that you saw where we've brought the embodied carbon down to almost nothing for new construction, all those materials are already available. So we don't have to invent new materials. Of course, we will invent and evolve our materials, but what we want to do is pick the best available options today. Okay, MCE2 follows the conventions of life cycle assessment by showing users the global warming potential impacts of producing a product along with the total biogenic carbon storage. You'll find those figures beside each other in the emissions and storage columns in the tool. So again, so we have emissions per unit volume of that and storage. So if you take this number and you subtract the negative number, you get a total for 100 square meters of loose wool fill with R 4.4 per inch, 100 square meter of wall assembly, your CO2 impact is 710 kilograms of CO2 emissions. These figures are then combined to get the net emissions column by subtracting the amount of stored carbon from the emissions created in the manufacturing of the product. If emissions are greater than the storage, the net emissions number will be positive. If the amount of storage is greater than the emissions, the negative number will show up in a green color. This negative number will lower the total emissions for the whole project, reflecting the fact that the carbon is stored in a home, reducing its overall climate impact. So we can, just by scanning these spreadsheets with thousands of entries, we can look for green entries and go, hey, these are carbon negative materials. I wonder if any of these would be suitable. Okay, I think we agreed that we'll go to the end for questions. So well, that's the end of the introductory section. Again, if you are, and I'm not flipping back and forth, I see there's only one question in the questions, but if you do have a particular question, try to make reference to the slide in which the question occurred. And since I see only one in here, does MCE square ever consider soil in this equation, either being imported or maintained on site? And the short answer is no. Okay, so those calculations, and really all we're doing in MCE is we're comparing the total emissions for those first three product categories, A1 to A3, that cradle to gate scenario. The reason that we the reason that we've chosen to calculate only the cradle to gate, I'll remind you, it's 85% of the emissions are in that portion where we're extracting the raw materials and manufacturing them into a product. So we don't know how far your site is away from that manufacturing to get the transportation to your site or your construction methodology. If you are to go on and study life cycle assessments, your assessor will be able to make those evaluations for your on-site grading activities and so on, water and other things such as that. Okay.
Perfect, Tom. So if I can just jump in, just a quick reminder for our members, if you do have questions, please feel free to post them into the Q&A window now, because Tom is going to address all these questions. Thank you.
Great. And yeah, good. Thank you, Felix. So I'll let those build up. I see 4 more have popped up since I answered the first question, but for the sake of timeliness, I'm going to continue on with the presentation at this point. Okay, so a little orientation and demonstration with the software. I'm going to provide you with a URL to download it. Feel free to do that. In a few minutes, we're going to take a 10-minute break. That might be a really good opportunity for you to download the NRCan software. Let me just see if I can get this URL and I can post it in the chat box for you. And by the way, for the purposes of this this course, you don't need necessarily to have the software open in front of you. I'll show you the pages of the software that we're working on, and you can look at it later in your own time. So again, it's an Excel spreadsheet. This will take you to the current downloadable software and also a user manual for it. And as indicated, that that link has been placed in your chat. Once you've downloaded MC Square, you'll need to click on the icon to launch the tool. On your first use, you will be prompted to enable content. So again, this is anytime you open a smart spreadsheet in Excel, it's going to ask you, to enable the content. And you must do this for the tool to be functional. So the little enable content button up here that'll pop up as part of your Microsoft operating system. Okay, so if you're following along, or if not, this is the first thing you're going to see, that it's important to get familiar with these spreadsheets, navigating MCE as it follows all the norms of an Excel spreadsheet application. Navigation through the tool is achieved using tabs along the bottom of your screen. There are a lot of tabs in MCE Square, so you'll need to scroll using the left and right arrows or the 3 dots. And they're talking about down here. Or the 3 dots over here, so that we can scroll along these tabs. The tabs with the gray background are general information tabs. They include a cover page, a license page, introduction on the left side of the scroll, and a glossary of terms and a table of energy greenhouse gas factors on the right side of the scroll. Please explore all these tabs when you have an opportunity or a need to do so. We won't be covering these tabs in today's courses. The user input sheet is an important part of using MCE Squared and exists at the left side of the scroll. This is where you'll input important project information and all of the required dimensions for your building model. In the middle section of the scroll are tabs that represent each of the major assemblies of a typical residential building, starting with footings and slabs, so bottom up, moving through each unique assembly required to build a house. These do not need to be visited or completed in any order, and only those relevant to your model need to be completed. Lastly, on the right side of the scroll are the review, results, and scenarios tabs. These provide results of a modeling exercise in the tool and are visited once all the dimensions and material selections have been entered. Okay, so as indicated, I have a slide here for a 10-minute break. Just looking, I'm almost exactly halfway through the presentation, so we're, okay. I might perhaps make a suggestion to take a 5-minute break so that we have more time for Q&A at the end of the session. So if I could suggest that I have 11:54 on my computer, I'd like to resume at exactly noon. All right, welcome back, everyone. I'm going to go ahead and start moving through the presentation here momentarily. I did have a chance to flip through some of the questions. Great questions, by the way. One of them that did pop up that I'll just take an opportunity to answer. There's a question as to how can wool insulation have a negative or a carbon storage number. I've jumped into the tool here. You can see wool bat insulation on this line, other natural fiber insulations for 100 square meters of wall area. It will sequester 530 or call it 540 kilograms, but it also emits 1,000 kilograms. So it has a net positive emission rate. It's not a negative number for wool. You might have been looking at wood fiber perhaps and read it as wool, but the two numbers that we have for wool in the database are both positive numbers, but the negative number I think is probably the carbon that's trapped within the wool that's been harvested and turned into a building product. But we'll get back to all of your questions at the end of the presentation. Okay, so if you're following along at home, great. You can do that as I walk you through this, or bear in mind these slides should be made available through the OAA, and you can take your time working through these scenarios at your leisure at home after the instruction today. So step one of using MC squared involves opening the user input sheet and filling out the required relevant information. So you have to enable the content, and you're also asked to select French or English language. Once you select English as a language, it goes through some strange gyrations, but converts all the verbiage to English as opposed to French. So on the right side of the scroll are the review results and scenarios tabs. These provide the results of the modeling exercise in the tool and are visited once all the dimensions and material selections have been entered. If you're working with a model that's already been created in HOT 2000, you can use that large green button that says import relevant H2000 files and use that to import your data. Doing this will automatically fill out the project information section and all of the dimension cells that are colored blue. The HOT 2000 import will also fill in the operational energy and emissions area in the top right of this information, and will be used to help understand the relationship between operational and embodied carbon. So as soon as you input that data, these cells will start to populate. It's important to check dimensions that are imported from HOT 2000, as there can be issues or inconsistencies with these dimensions, especially for knee walls, step foundations, and other complex geometries. Your embedded carbon model will not be accurate if these dimensions are not accurate. The dimension cells that are colored yellow will not import automatically from HOT 2000, as they are not elements of the home included in the energy model. These yellow cells, if applicable to your model, will need to be entered manually. If you're not working with a HOT 2000 file, then all of the project information cells and dimension cells that are applicable to your project will need to be entered manually. You will need to refer to the project plan to set to obtain the dimension information. Note, in version 2 of MCE, you will need to enter a province in the appropriate field to trigger the relevant EPDs for concrete in that province. Our first exploration of MCE squared will be to perform a simple material comparison. This is one way of using MCE squared and requires the least amount of input from the user. For example, we'll compare the MCE of different types and brands of wall cavity insulation for exterior walls. As you recall, MCE square operates by multiplying the material quantity by the global warming potential factor from the EPD. the environmental product declaration. In order to see any results in MCE squared, you need to provide the tool with a dimension it can use for this operation. For this example, we want to compare exterior wall insulation, so we need to provide a dimension on the exterior wall area cell, as highlighted on the slide. For the purposes of comparing materials, the dimension doesn't need to come from the set of plans. You can enter any number. I suggest using 100 for basic comparisons, because the results in MC square are rounded. Using a smaller number like 1 or 10 could provide slightly skewed results. So we're going to calculate the embodied carbon for a wall assembly that's 100 square meters of material. And then if we take insulation A out and replace it with insulation B, we can calculate that same wall assembly for the same R value and see if the embedded carbon increases or decreases. So that's where this 100 square meters is coming from. Okay, so that's input where on your user input sheet, which is identified down here on the tab labeled user input sheet. So it's helpful to understand that these results you'll see in MC squared provide linear comparison. This means that the relative difference between the results will be proportionally the same whether you're looking at 100 square meters or 20,000 square meters of wall space. Once you enter the dimension into the cell of the user input sheet, it will automatically be imported to the appropriate building section tabs. Since we entered 100 square meter in the exterior wall area cell on the user input sheet, let's now navigate to the exterior wall tab, EXT walls. Clicking on EXT walls tab will bring us to the exterior walls page as seen on the top of the page. And the heading here, exterior walls, corresponds with the tab exterior walls. On the right side are the review, results, and scenarios tabs. These provide results modeling exercise. Every building section in MCE squared is organized the same way. Let's take a moment to get familiar with how some of these pages are set up. The name of the page is always at the top. We have our, each page is organized in a hierarchy of material categories, colored in dark blue. So here you'll see wood frame walls, steel frame walls, wood I-beam framing, so on and so forth. Okay. And our calculations take place up here. So again, it's going to calculate, once we select the materials, it'll calculate based on these values. Over here, you can see these are zeros. That means these have no carbon capture and storage capability baked into the cake there, so to speak. And by the way, I look forward to that discussion on lumber. I saw that in the Q&A also. So in the product list, so we've gone into the wall steel framing 2x6. Oops, where's 2x6? Okay. And then there's a whole range of options here. So we can, as previously discussed, use the industry average. Maybe if we're early in the design process, maybe we know exactly that we're going to use merino ware, load bearing 16 gauge studs. We can get the specific EPD for that material. So in the product list, you'll see information about each specific product. It includes product type, steel studs, load bearing, manufacturer, product name, product specifications. Before making product selections, be sure you understand the product information and ensure the project is suitable for the project's requirements. You still have to make design decisions, right? If MC square provides an average result for all the products in the category, it will appear in light blue at the top of the list. In this example, average is based on all 5 unique products in this category. This is appropriate selection to make if you're not certain of the product that will be used, or if the product you know will be used is not on the list because it does not yet have an EPD. So, okay, no EPD yet. Well, we can still get close, right? And the key here is not to chase the decimal places. You know, if we can get around 10%, we should be pretty happy. Okay, so let's take a look at the yellow cells on each of the building section tabs. For some material categories, you need to make additional input before seeing any results. The yellow cell in the dark blue material category row indicates it's a required input. This is because MC square needs an additional factor in order to calculate the material quantity. For example, framing spacing will be needed to be specified before MC squared can calculate the volume of wood required for a specific wall area. Other additional inputs include R value for insulation products, wall thickness for poured concrete walls, and concrete or timber volumes for piers and joists. A percent column is also colored yellow. The default value here is 100%. You can see that already auto-populated. You can use this percent to adjust the material quantities. For example, a house is likely to have multiple types of flooring. And the percentage function can be used so that each flooring can be selected and the correct percentage of the total floor area is used, i.e. 50% carpet, 12% tile, 38% hardwood. The percentage function can also be used to make adjustments to material quantity if the appropriate option is not available. In the product list, for example, the default products for hardwood flooring are 3/4 inch thick. If you're using flooring that is 5/8 inch thick, you can enter 83% in the percent column to reduce the quantity of material that this will adjust the results proportionately. It's suggested that you make your own notes when adjusting percentages to track your logic for making adjustments in the case of the model changes in the future. Finally, if we're going to use that material, we select 1 in the select column, which is right here. So if I put 1 in here, that means I'm going to use 100 square meters, 100% of this type of assembly. Okay. And once I put that in, number 1 in there, it will calculate this value for me. So in this case, the 1 was entered down below. And this net for the material is this minus this. So 178 minus 0 is 178. It's red. It's a positive number for 100 square meters of that assembly. Okay, step 2. Now that you're familiar with the contents of a building section tab, we can continue our exercise of comparing cavity insulation types and products. Scroll down to find the cavity insulation category in dark blue. So this is on that same exterior walls, right? And you have to scroll down and you're going to expose a dark blue heading that's cavity insulation. So we got fiberglass bat, blown in bat, mineral wool fiber. Again, that's rock wool, not a sheep's wool. Cellulose, which is carbon negative, and wood fiber, so on. But it doesn't know how much until we know, or we tell it the R value. We can put in 1 value here if we want 20 for all these different assemblies, or we can put in unique R values for each of these different assemblies. So you're going to scroll down and find that cavity insulation category. You're going to need to provide an R value as indicated in the yellow cell in order to complete the calculations and see any results. So we enter in 20 in the top one. So that auto-populates all of the assemblies with R20. Anytime you see zeros in the emission column, it's likely because you've not entered the required factor like an R value. With the R value at 20 in this case entered, you'll see the results per 100 square meters of each insulation type and the product at R20. As mentioned earlier, black numbers indicate net emissions, green numbers indicate net storage. The lower the number, the lower the climate impact of that material type or product. Also, as mentioned earlier, the light blue average in each product category is calculated based on results of each unique product in that category. The final step in the process is to make the product selection. After reviewing the products and ensuring that the specs are appropriate, you select the chosen product by typing the number 1 into the select column. It's kind of like a check mark, right? It just tells it that's what the assembly we're looking at. When you press enter, you'll see that the selection is confirmed by the result appearing in the cell colored orange. Once this has happened, your selection has been made and the result has been added to the subtotal for the building section tab and to the review and results tabs automatically. One of the most frequent questions about MCE squared is why so many results are 0. So we just talked about that a moment ago. Most common reasons, again, users not filled in one or more of the required cells, the yellow cells, to complete the calculations. So dimensions haven't been entered in the cell area for user input. That's another good place to start to look. And additional factors such as R value, wall thickness, framing spacing have not been entered in the yellow cell material category bar. If information has been entered in all required cells, try saving the document and then trying again. As previously mentioned, there are 13 different building section tabs. Depending on the analysis you want to perform in NCE squared, you'll need to visit as few as 1 or as many as all of these tabs. You may only need to complete entries on one building section tab if you're comparing materials in a category, like we did insulation for insulation. You may need to complete entries in 1 or 2 tabs to complete different assemblies or material swaps within the same assembly. You may need to complete entries on all the tabs if you're modeling a whole home. Note, MCE squared is used to analyze a retrofit as well as new construction. For retrofits, complete entries on all building section tabs that are relevant to the scope of work of the renovation, what you're adding to the structure. What is already there, that carbon's already in the air. So we start at 0 and we add the embedded carbon for the materials that we're adding to the existing structure. It could be as simple as comparing windows, if new windows are the only work on the project, or it could involve entries on multiple tabs. For example, roof, exterior walls, and foundation if insulation is being added in all 3 assemblies. And on a retrofit, you would want to add insulation in all 3 assemblies. Here's a home with a basement. You know, we've got about 20% of the energy loss through basement walls and floors. That needs to have continuous insulation. Our walls are about 40%, and our roof can be about 40%. In London, Ontario, we used HOT 2000, and it determined that we wanted R20 for the basement, R28 for the walls, R60 for the attic insulation, and R20 under slab insulation. So now all of a sudden we can populate these R values into the carbon estimator and the type of insulation that we're choosing and make an appropriate low carbon selection. Once you've made all the material selections on the relevant building section tabs, you can proceed to the review tab. Here you'll be able to see all the material selections you've made on your model. On the left side of the building sections that are color coded, so you can easily see all the materials in that section. So all the floors in this case are brown, interior walls, cladding, exterior walls, all color coded. Okay. The review tab is very useful for doing quality control as the review of all the materials without needing to scroll through each building section. You can quickly see if you've missed any materials, double counted, or included irrelevant materials. At the top of the review tab, you'll see totals for net emissions, and storage. Okay. And that's what we're actually emitting. The carbon emissions in total are this minus the negative that we're sequestering into the building tab. Note that you can continually adjust models in MCE squared. If you want to make changes after seeing the review tab, you can revisit any building section tab on your model, make changes to your material selections. Every time you update selections on your building section tab, those changes will automatically be reflected in the review tab. Step 4, the results tab. As with any Excel file, you should be able to save your work continuously as you progress through the building model in MCE squared. The first time you save, use the Save As function in Excel to create a uniquely named file for your model. If you've completed your quality check on the Review tab, you can move to the Results tab. Here you'll find some reporting templates that have been filled in with your project's results. Note that several areas in these templates were meant for whole house models and will not create an accurate picture if you've been comparing materials or assemblies. On the Results tab, you'll find that project information summary populated automatically from the user input data sheet or HOT 2000, space to insert a photo or a drawing of the project. The results scale showing the material carbon intensity of the project related to according to results from previous studies across the country. That's this, you see these on, if you buy a refrigerator, for example, it shows that this is 138, and it's pretty much right in the middle of the range between really good and really bad homes. Kind of a quick visual. So we've got the project notes section there. We can enter in specific notes that we've had, scenario 1, or things that we've had to change. Maybe we've had to customize some fields. And then a project emissions timeline, which is down in the lower right corner. We'll spend some time looking at this. All these calculations are done based on a 30-year horizon. And the reason is 30 years is not as long as that house will last, but it's about as far out as we can reasonably predict emission factors for grids. So we know they're going to be improving, but we don't know how much. So we're only extrapolating this out 30 years. If we did it for 50 years, it might give us misleading results. The second page of the Results tab provides a graph showing the extent of the emissions or net storage broken down by building section. This enables you to quickly determine which assemblies contribute the most to the MCE of the project and suggest assemblies you may want to revisit in order to make improvements. So what did they just say over here? Emissions by element. Okay, so this is footings and slabs, has the highest emissions of, oh, there it is, 8,779 kilograms. Maybe we should go back, if we want to lower the carbon emissions of this entire structure, I would go back and look at the carbon of the concrete mix that we chose. Maybe we can select another concrete mix from the list of opportunities. Again, gives us the required strength, but might be produced using supplemental cementatious materials, admixtures, which are oftentimes forms of toxic waste like fly ash to take up space in the concrete mix so that we're not using raw materials to do the same function. And the second graph over here gives you the top 10 most impactful individual materials. So these are assemblies on the top, the bottom are individual materials. In this case, XPS foam board was the highest chosen for this design. Maybe, you know, we need to look at alternative insulation techniques instead of the foam chosen to lower the material carbon emissions. Both of these pages print out on an 8.5 by 11 sheet of paper. You can copy the results from this Excel spreadsheet into any spreadsheet and calculate your own graphs and depictions. Down here, it's really just giving you a sum total. Scenario 1 had this much carbon that we've gone through in scenario 2, made some adjustments, and it shows you that now you've lowered the embodied carbon that much. The color coding is hard to read here, but this sort of burnt orange colors are the exterior walls by way of an example. So a relative proportion of what the exterior walls are contributing to the overall carbon. Footings and slabs, well, those are big, really big initially. And here they went with a TL30 lower concrete and XPS and reduce the carbon emissions. We can do up to 6 different scenarios using the scenarios tab. You can obviously reset the calculations, or you can reset all the scenarios, or you can save a particular scenario and go back and what if again. When we were energy modeling a retrofit, what we did is we picked a target energy reduction of 70%, and we were able to try all different materials, assemblies, windows, till we got to a 70% energy reduction. Okay, so we're nearing the end, so I'll just save again the questions for the final end here. Let's take a look at, you know, the ways that we've just discussed. So we can use on material only. We can compare one type of insulation or one type of concrete to another, one type of flooring to another. You know, flooring such as linoleum, carbon negative. Flooring such as ceramic, very heavily carbon positive. We can do assemblies, and we did, you know, an assembly of 100 square meters so that we could compare 2 different assemblies, apples to apples. We can do a whole building, and we can do that early in the design stage. We can do that during detailed design and as the design refines, or we can do whole building plus hot 2000. The nice thing about that is the energy, operational energy is done. You can upload it into MCE squared. You can optimize your materials, and then you can run those back through hot 2000 to see what it does to your operational emissions. Say, for example, if I put in more insulation that's carbon positive, my operational carbon will go down because I'm putting on more insulation. Where's that trade-off? Where is too much insulation? A bad choice, because it's going to create more carbon than that more insulation will save operational carbon.
Thank you, Tom. If I can just jump in, we have reached the official end of the webinar. And if members need to log off, please feel free to do so. But Tom, I hope you can finish the presentation and maybe go through some of the questions that have been posted into the Q&A window.
Okay, let's shift into that right now, because I'm sorry, time got away from me there. I don't know how that happened. I thought I was doing great. Okay, so I'm just going to scroll to the top. I've already talked about Matthew's question. How does, and the wool insulation, it does have some sequestration, but both the wools listed are carbon positive. Does MC consider the carbon impact, this is from Michael's question, of labor, methods, and installations into the building components? No, because it's only looking at A1 to A3. We've got to go through all of the building stages. That would be done as part of a life cycle assessment. Again, we're calculating A1 to A3 with this software. Are MCE square defined as various open or closed cell spray foam installations? Yes, there are, and also the blowing agents have been modified recently, and many of those material carbon emissions have dropped dramatically. So if you haven't looked at foam in a while, you might want to take a second look at it. How can we get the Hot 2000 programs? Ed's asking. You get it the same way you get the MCE squared program at that natural resources website. I think if you go back up one level to tools, it lists all the tools, including heat pump calculators. And then Lee, I mentioned the forestry industry, and yeah, that's kind of the whole discussion is going on here is, is it really carbon negative? And, we'll allow you to tweak that number in the future versions of the software. Right now, we've kept it out of the calculations. The thing just jumped on me when somebody added another question here. Okay. Okay, then there's some discussion about the link for the chat. And thank you, Melissa, for providing that. And more questions about the link. Are there any more real cowboys? I'm not sure about that. I've downloaded the software, but it has opened to French. Okay, so you're going to select English there, and it'll go through some gyrations. And thank you, Melissa, for answering that question as well. I get a message that cannot run the macro to translate to English. I've opened it several times on several computers. It's gone through gyrations, but every time it did open in English. So you might want to just re-download it and try that again. Sam's asking, we've completed a life cycle assessment on locally sourced air-dried timber materials in our region. Are we able to create? Yes, you can create custom entries. We're not really going into that today, but yes, you can create it. And I might be able to get to one slide after these questions just to talk about some of the limitations. It'll go quickly. Okay, yeah, someone's getting that cannot run the macro. And again, make sure that you have the cells populated that need to be populated. Are any home builders using these tools? Yes, absolutely. And, there are examples. Talk to your energy advisor. They probably have some for you, some examples. And again, these vary by region, so talk to a local energy advisor. Jonathan asks, or makes a statement here, many of the alternate materials or assemblies seem to be atypical. I wonder if it could make their way into these charts. Yes, we have another software program called CBAT, cost benefit analysis tool. And that also plugs and plays with these two software programs, not the subject of our talk today. Are fully insulated vertical walls adjacent to roof areas attics calculated? So again, it knows it's a wall. It knows that there's an attic above it. So it would do those R value calculations for the wall. In the attics, especially in retrofits, if you don't have stepped trusses, what we found to get the R60 above the exterior wall assembly, that we had to go with a 2-pound foam for about a 2-foot perimeter around the exterior of the house inside the attic to get that R60 value. Is there a way of inputting passive house model? No, but you could take the data from a passive house model and crank it into here, or you could just compare wall assemblies. And I believe Felix is going to make a copy of the presentation available to everyone.
Yes, that is correct. It will be sent out after the webinar.
Thank you. Okay, and Randy, but attic beside, I think I answered that question. And Brad, the English to French translation is not working. Okay, so file properties under security helps with that, apparently. These are tools mainly intended to be used by energy modelers or architect will require to submit. Well, they could be. You could use it as part of, say, for example, net zero certification. Your net zero builder and your energy advisor are going to do these calculations and these models, and all these models are going to be handed over to the service organization before you get your net zero certification. Awesome questions, and I thank you for those. I'm just going to quickly spin through some limitations on the software here. So just the square, again, this is for previous studies in Canada, are shown in material emissions are shown in both total amounts in tons of CO2 equivalent or the kilograms of CO2 equivalent per square meter of floor area, finished floor area from our earlier discussions. And the timeline plots this based on a 30-year use cycle. Most the mechanical systems in that will be changing by then. Again, the results, we go for the big ones, right? We're already sequestering carbon in the roof. Maybe we need to focus on, these areas. Why is the garage so high? Well, I bet it has a lot of concrete. Which categories? Again, footings and slabs are the #1 offender in this scenario. We're comparing things. We're not getting a total number for a life cycle assessment. In order to get a total life cycle assessment, you need to do a life cycle assessment, which is categories A, B, C, and if you're doing a whole building zero carbon life cycle assessment, it's also categories D. Okay, so there are always conditions. I have a saying that models are never correct, but they're often useful. Okay, so don't drill into the multi-decimal points. Look at comparative results, qualitative inputs, and if you're getting down to plus or minus 10%, stop. Okay, that's about as good as you can get. So other limitations, the garbage in, garbage out. So the uncertainty for environmental product declarations is somewhere between 5 and 25%. Remember, type 3 are the best because they're verified. Maybe we are using rules of thumb that don't actually have the correct materials in there. Maybe we haven't included for a waste factor. If I'm buying lumber and I'm going to have 10% waste, on that percent, I can just put in 110% instead of 100%. So it calculates the carbon that results from the offcuts. Missing material categories, that came up in the Q&A. That's the next slide here. You can add your own categories. So we don't transport it to the site because we don't know where your site is. We don't know what your construction emissions are because those are decided by the constructor. And there are no end of life emissions at the 30 years. It's just assuming that that building will be retrofit and continue to operate. No code, no building science. There's no substitute for knowledge. Okay, so again, we got a lot of data on structure, enclosures, partitions. We've got no data on mechanical, electrical, plumbing, appliances, interior finishes, millwork, or yard work. Why? Because there's a lack of data. Can you do that in your life cycle assessment? Yes. We can't do that because we don't know that much about your project. The missing elements. So the stuff that isn't calculated, but is still, we know has an imprint. We've given you some good numbers here. So for ductwork in an existing house or a new house, 100 kilograms of CO2 equivalent. Toilets and sinks. Why? Because we have to use ceramics and they get fired in furnaces. They are very carbon intense. So on and so forth. So per square meter, all of those things added up, roughly 40 kilograms of CO2 equivalent per square meter of finished floor space. So again, these A1 to A3 categories, this is what is in our wheelhouse for MC squared. The stuff downstream from that is not, and I talked about that, the transportation to the site and the construction of the building, but that represents about 5 to 10%. This is the big one, right? That's why we focused on that. Okay, where are you trying to learn? Compare materials. I find it, especially that visual comparison, green numbers jump off the sheet at you. Those assemblies, put a hypothetical 100 square meter assembly and compare 100 square meter assemblies to try to make some of those early material choices. If you have HOT 2000 and you've imported all the data, or you've input them directly, you can do whole building to whole building. Again, A1 to A3 though only. What about renovations? Same thing. All we need to do is add the materials that we're adding as part of the renovation. So it's air sealing, insulation on the outside, and cladding. We need to shed the rain. We need our wall assemblies to dry when they get wet, building science stuff, right? Only use the sections that apply. If you're not doing a garage floor, you don't need to do that tab as an example. So when to do this? I say early and often. So in the schematic design stage, why? Because we can make sweeping changes in the schematic phase that don't affect construction costs. Why? As the design evolves, again, you're going to pick structural materials, maybe details, assemblies. And then at construction time, it's time to order the concrete mix. Let's take a look at the EPDs and see what suitable mix is the lowest carbon for our project. Who benefits? The client. The project comes in on schedule and on budget. The buildings are more full because the occupants are healthier. The design team is done through an integrated design process, which could be another 3-hour presentation. And then again, if you're applying for a LEED certification or net zero certification, some of these numbers will satisfy those requirements. Repeat offenders, and I've talked about them: concrete, insulation, cladding, interior surfaces. Look at these big ones: concrete, insulation, cladding. That's roughly half of all of the emissions. Up here, roofing's 2%. You might not be able to drive that much lower. Material substitution. So again, we can substitute with the best available materials. Oops, best available. We get a 44% reduction in operational carbon. Maybe the material and our material carbon has gone down also. Best possible, we can take it down to virtually 100% reduction, 96% reduction. So how do we implement this in stages? Year 1, take a look at your concrete mixes, make improvements there. Year 2, take a look at your insulations. Try to pick one that's your standard insulation, your go-to insulation that is low carbon. Same thing for your drywall. Year 3, or you could do them all in year 1, right? And be ahead of the rest of the plant. Year 4, one insulation, okay? Cladding to best available. Year 5, change the flooring to best available. Change one insulation type. And we go from 200 kilograms per square meter and our baseline to almost a little more than half of that, 40% reduction systematically. City of Nelson, BC, material selection and quantity is a leading factor driving the carbon intensity, higher or lower, okay? These are where step code is, step 4 is basically net zero. Step 5 is zero energy. Not all buildings are created equally. So high carbon intensity plus 4 tons per year gives us a total of 188 tons. At 40 tons of material, at 0.2 of a ton operation per year gives us a total of 46. If we start with low embodied carbon materials and add our 2 tons per year, it gives us a total of 18. What was that first one? 108 or something. So we're about 10% of what the other ones. Other things that you need to have on your radar: energy efficiency, including all the appliances that you're putting in there. Health and safety, we don't want any toxic materials in our buildings. Waste needs to be eliminated, minimized at best. Durability, how long is it going to last? Does it make more sense to have a high carbon material if it's going to last for 100 years? Good question. The software can't determine that for you. Cost, I mentioned the CBAT. So in this software, we don't have the cost correlation, and labor impacts, especially after COVID, we're quite aware with those. Chris Magwood is the originator of much of this work. I've been working with him closely. We're actually developing new training for this course, but Builders for Climate Action have a number of reference documents for your illumination later on. And finally, a big thank you to the Government of Canada for the work done here on behalf of all Canadians. Okay, I'm going to stop the share. I'm going to apologize for going 15 minutes over my allotted time frame. I think I answered everyone's questions, unless a couple snuck in there at the end. Just having a look. Yeah, the correlations of less fire. Oh, there's a good one. Simon's is a final point here. Is there a correlation to less fire resistance qualities as we move away from conventionally used concrete? Yeah, that's a whole nother thing. So when we think about resiliency, these buildings can't blow away. We don't want them to burn down either. Concrete's great for that. Is it the only option? No, because there's an array of concrete mixes and or other wall assemblies. And my friends at NRCan LEEP team are just about to publish 7 new wall assemblies, some with resiliency in mind. I'll just ask if there are any further questions. I'm at the end of my show, so I'm going to sign off. And thank you for your time. It's greatly appreciated. I apologize for going 15 minutes over. I hope you found today's session interesting. Grab that program and start playing with it. Look at the numbers through the categories. All of a sudden, you'll know products. You'll look for products that have low or negative carbon numbers. Okay, so I'm going to sign off for now. Thank you, Felix, for your ongoing support at OAA, and make sure that you keep your continuing ed up to date.
No, thank you, Tom, very much for today's great presentation. And we conclude this webinar. I would like to draw your attention to several important announcements before we finish. Our next webinar is scheduled for next week, February the 15th, under the title Fabrication Design and Constructability for Mass Timber Structures, and we invite you to join us to this webinar as well. The OAA will report your participation in this webinar to your transcript. Therefore, there is no need for individual reporting on your part. We kindly ask for your patience as we process and confirm the accreditation of your hours within the next few weeks. Additionally, all attendees will soon receive the presentation file via email, along with a link to submit your feedback, which we highly value. Once again, thank you very much for your attendance and have a productive and pleasant remainder of your day. Thank you very much, Tom, again, and see you next time.
My pleasure. Thank you.
Bye-bye.